Hi everyone! In today's video we are going to do a very brief overview of exponential and logarithmic functions. Our goals today are to be able to, number one, answer SOL style questions, and number two, to have a basic understanding of the general shape of exponentials and logs so we can use that information when we graph for regression equations, which will be coming up in another lesson soon. So we're going to be able to distinguish between exponential and logarithmic growth and decay. We're going to be able to analyze the characteristics of both functions, meaning discontinuities, domain, range in behavior, and intercepts. And we're going to use the logarithm and natural logarithm buttons on the calculator to get our graphs. And then we're going to use those graphs to answer characteristic questions, but also to make a system of equations to solve exponential and logarithmic functions. So first, let's just talk about the general form. You'll notice for exponential functions that the x now is in the exponent, and that's why it's called an exponential function, because the independent variable, the x is in the exponent. Notice that you do still have h and k and an a value, just like we have with all of our parent functions this year. Exponential functions are generally going to be this kind of hockey stick shape. If they are an increasing line, like this one, that's going to be a growth. And if they are a decreasing line, like that one, that's going to be a decay. And that happens when the b value is a number bigger than 1 versus a number smaller than 1. So just by knowing what that base is, b, that's the base that has the exponent of x, we'll be able to tell whether it's an increasing or a decreasing line. The other important factor of exponential functions is that they all have horizontal asymptotes, meaning that this hockey stick shape is going to get really close to that asymptote, but it's not ever going to touch it. It's just going to keep going, in this case to the left. The horizontal asymptote on an exponential decay is going to mean that this bottom piece is getting really, really close to that asymptote, but never crossing over it. So in both of these rough sketches, neither one of these is going down to negative infinity. On this one, on the left, it's getting close to that asymptote, not negative infinity. And this one, as x approaches positive infinity, it's getting close to that asymptote, not negative infinity, because it's not crossing over that asymptote to go down forever. With logarithms, logarithms are the inverse function of an exponential. So all of the x and y's flip positions. So what that means is our graph is going to flip, and we're going to have a graph that looks like this. And it's going to have a flipped asymptote, so it's going to have a vertical asymptote instead of a horizontal. Now in our exponential functions, the k value is what gave us our horizontal asymptote. In our logarithmic functions, it's the h value that's going to give us our vertical asymptote. Now the other thing that I want to mention just briefly here is you'll notice that I've given you the parent function for a log base b. This b is going to be some number. If you just see a problem where it says log of x minus 2, maybe you're working with something like this, you can assume that if nothing is written there, that's a log base 10. And there's one special type of logarithm called a natural log, and we're going to use ln whenever we see a natural log. We'll talk more about this log base 10 versus log other bases and natural log in Unit 8 when we do it fully, but for now you just need to know that there are going to be a couple of different things that might come in that spot in the equation, and they're all logarithms. Okay, so let's look at some graphs. We are going to use Desmos to get these graphs, and then we'll talk about some of the characteristics. Now, I do want you to notice that because the x is in the exponent, this is an exponential function. And because the b value, that's the 2, that's the base, is a number larger than 1, this is going to be an exponential growth. And that means we're going to have an increasing line when we graph it. So let's go ahead over to Desmos and graph this function. All right, so we're going to y is equal to, and then I'm going to type a 2, And then you can either use your exponent button here to get up into the exponents, or you can hit the Shift 6 key to use that caret mark. Either one will get you up into the exponents, so you can type x minus. Did you see how that just, or I'm sorry, it's a plus. Did you see how that plus just moved outside of the exponent? It's not an exponent anymore if I keep typing down here. Because of that, what that means is Desmos needs us to use parentheses when we're up in this exponent. So I'm going to hit the up key. I'm going to go back to the other side of the x, and I'm going to put parentheses there. So when I type plus 1, it all stays up in the exponent. It's not down here where it would be part of our bases. We want it to stay up in the exponents, and those parentheses are going to be really important. So let me just change some of my modes here to make it a little easier to see. Okay, so some things that I want you to notice here. We have an increasing line, which is what we expected. That's an exponential growth. And if we hover, we can see some special points. It looks like there might be, 1, 4 is going to be an ordered pair. And we can get other ordered pairs. It looks like if we hover here some, yep, there it is. -1, +1 is going to be an ordered pair as well. And as you scroll along this side here, do you see how the y value is getting really close to 0, but it's not ever actually 0? That's going to happen no matter how far we go out, because when we have an exponential function, we have a horizontal asymptote. So Desmos even can't comprehend how close it is. So you see it's at 0.001. Eventually when it gets out here, Desmos is just going to say, it's so close to 1, I have to round it, and I can't. But it's not actually touching 1. It's 0.000000001, and so on out here. So let's get a rough sketch on our board here. We had -1, 1, 0, 2, and 1, 4 as points, and that asymptote was at 0. So we have an exponential function that looks like that. Now let's look at the second one. This one is going to be exponential as well because the x is up in the exponent. Oops. But this time, because the base 1/3 is less than 1, this one's going to be exponential decay, and that means it's going to be a decreasing line. It's going to look something like that with an asymptote somewhere. So if we go back over to Desmos, and this time let's put our 1/3, and then I'm going to go up into my exponent, and I have just an x, so I'm not going to need the parentheses there. Now, if you wanted to put your 1/3 in parentheses, so it looks a little bit more like maybe what you were expecting, you are welcome to do that. It will give you the same graph no matter which way you do it. Notice we do have a decreasing line here. If we look at, if we take our cursor along the edge, we can see it looks like we're going to have, yep, -2, 9 is an ordered pair. We look like we're going to have a -1, 3. Yep, there it was, -1, 3. We've got the y-intercept, and if we go far to the right, you see how, again, it's rounding it to 0 because all of these decimals get so small it has to round because it's run out of decimal places. So that means our horizontal asymptote is going to be at 0. Oops. And some of our ordered pairs were -2, 9, -1, 3, and 0, 1. So that's going to give us roughly that exponential decay shape, and then we could answer questions about characteristics. Let's do a couple of logs to make sure that you know how to plug those into the calculator as well. So for this first one, it says log, so I know this is going to be a logarithm. Let's go ahead and plug that into Desmos. So this time, to get a logarithm, you're going to go over to the Functions button, and under Miscellaneous you have three options for logs. There's the log with no little base number, there's log base A, and above the log base 10 there is a natural logarithm. These three buttons are the ones you're going to use most often. Now because the problem just said log and then parenthesis x minus 2, we're going to use just the log base 10 button. Notice it's not going to put a little number there. So I'm going to type x minus 2 in the parentheses, and then I'm going to put my plus 3 on the outside of the parentheses. Notice that I have an increasing line. This one is again going to be a vertical asymptote because it's the inverse of exponentials, and the flip-flop of a vertical is, or a flip-flop of horizontal is vertical. So you'll notice here, if I slide my cursor along, I can see a couple of points that it looks like I'm going to be able to graph pretty easily. And then you'll notice also as we go along that we are getting really close to having a vertical asymptote at 2. Notice that the x-intercept is really close to 2. And as we get further along, see how it says it's undefined? That's because it's not actually touching the 2. It's just getting really close to it. So on our graph, we have a vertical asymptote at 2. And a couple of the ordered pairs that we found were, I think 3, 3 was on there, and 12, 4 was on there. So that's going to be way out there. And then we're going to draw from there. Ideally, we'd have 3 points. It's kind of hard on this graph. The grid's not really big enough for that, so we'll just leave it with the 2 that go off grid. Okay, so for this next one, it's a natural logarithm. That's what the LN stands for. Now, I do want you to notice that there are not parentheses. Did you notice these parentheses? The log of x minus 2? This one doesn't have parentheses, so it means that this minus 1 is outside of the parentheses that aren't drawn, like this x plus 3. So this one is the natural log of x minus 1. So we're going to have to be really careful with how we plug this in. If the number value is supposed to be inside of the logarithm with the x, then it's going to be shown with parentheses like it was in that previous problem. Okay, so let's graph this one. This time, because we're doing a natural logarithm, we're going to use a different button on the functions. We're going to use this LN. Notice it gave me my parentheses, so I can type my x, and then I have my minus 1 on the outside. Again, we have an increasing line because this is a logarithmic growth. We have an x-intercept, which is not particularly a pretty point. If we run our cursor along, we can see that we get to an error message when we get down here. I can't click on anything and get a number. That's because it looks like it's getting really close, if we round it, to 0. So that means that we have a vertical asymptote at 0. And some of those other points that I saw for this logarithm, whoops, were 1, -1, and then there were really ugly ones, like 2.7, I think it was. So we'll put that there. And then 7, let's go like 3.9, I think it, or 7, yeah, 7.39 up at 1. So like there. So that one's pretty ugly. We've got some decimals in there, but that's our rough sketch. Okay, so let's just do some characteristics now. We're going to use the graph to help us figure these out. So let's look at this first one. This has an x in the exponent, so that means it's going to be exponential. And because the base is a 2, that means it's going to be a growth. We know then that because it's an exponential growth, it's going to be increasing, so it's never going to be decreasing. We also know because it's exponential, it's going to have a horizontal asymptote, which means there is not going to be a vertical asymptote there. Now let's look at our picture and see if we can answer some of these other questions. All right, so the problem was x, or 2, raised to, and then I'm going to use parentheses here because I had x plus 5 in parentheses there. Okay, so let's find our picture. There we go. All right, so we have a horizontal asymptote at 0, it looks like, because it's not getting any closer horizontally there, or it's not actually touching it. So then let's think about our domain. Our domain starts on the far left because this side goes infinitely to the left. So that's negative infinity. And on the right, it's going to go to the right really slowly, right? But eventually, if I go up enough, it is going to keep moving to the right, and it's going to have to go way up high to get out to like 50, for example, but it will slowly get there. So that means it's going infinitely to the right as well. So our domain for this one is going to be negative infinity to positive infinity. If we think about our range, though, this one has a bottom. It doesn't ever touch or go below 0. So our bottom is going to be 0, and it's going to go up to positive infinity. So for my answers here, my domain is, negative infinity to positive infinity. My range is 0 with a soft bracket because it doesn't touch the asymptote to positive infinity. Now this one was increasing from the far left to the far right. It's increasing everywhere. So that's negative infinity to positive infinity as well. The end behavior, as x approached negative infinity, remember it looked roughly like that, it was going, y was approaching negative infinity because it went infinitely to the left. Or sorry, that was a mistake. We're talking about downness here, right? As it goes to the left, the y values, they go down, but they get stuck at 0 because it doesn't cross over that asymptote. So that asymptote piece is really important for our end behavior here. If we look at the right-hand side, as x approaches positive infinity, the y values are just going to keep going up and up and up. So that is positive infinity on the right. If we were to look back at that graph for x and y intercepts, remember that this doesn't ever touch the x-axis because that's where the horizontal asymptote is. That means then that there's not going to be an x-intercept. But we can, if we click on our line, see we are going to have a y-intercept at 0, 32. So let me write those down. The x-intercept is going to be none, and that's because of the horizontal asymptote. And the y-intercept was at 0, 32. The horizontal asymptote, we already said, we're going to write it as an equation. Y is equal to 0 because it never crosses the x-axis because of that asymptote. Okay, so let's look at one more of these to do some characteristics. This one is a log, and you'll notice that it has this 4 down in the bottom. That means this is log base 4 of x minus 1. So when we put this into Desmos, we are going to have to use that different logarithm button. So if I clear that out, I'm going to zoom back in a bit. When I put y is equal to, and then I go to my functions, miscellaneous, this time I'm going to choose log base a. When I do that, it gives me a little spot here to put the base of 4, and it also gives me the parentheses so I can type the x minus 1. Okay, so here's our graph. Looking at it, remember we have a logarithm, which means we have a vertical asymptote. We also look like we have a x-intercept at 0, 2. This vertical asymptote is going to be happening at 1 because it gets really, really close to it, but the x values don't ever go past that 1. In fact, it disappears. This is when we have that undefined part. So, because this is a log base 4, that means it's a logarithm. Okay, we had said this one has to have a vertical asymptote, so it's not going to have a horizontal one. And we said that that was at 1 just a moment ago. I think we also talked about, what did we talk about? The x-intercept, right? We said that was at 2, 0. And this one didn't have a y-intercept because that vertical asymptote was at 1. And that was preventing it from ever getting over to the other side of the x-axis, right? It never touches the y-axis. So that one is going to be a never or none. Okay, so let's think about domain and range, or let's do increasing, decreasing. Remember, we're reading from left to right. This one is always increasing that way. So it is never decreasing. The increasing starts at the asymptote, which was at 1. So that means it starts increasing at 1 and it goes all the way to the right. The domain for this one is not going to be all real numbers. Notice that it starts on the left at the asymptote. So again, that's going to start at 1 and go all the way to the right. This one does have a negative infinity bottom and a positive infinity top, all real numbers, because this left side goes down forever and this right side goes up forever. So we have all real numbers for our range in this one. The only other thing we need to do is end behavior. So as x approaches negative infinity, that's the far left side of the graph. Well, if we look over here at the left, there's nothing over here. The y value does not exist. I'm going to write D N E because there's no graph over there. The graph doesn't exist over on the left-hand side. As x approaches positive infinity, though, the right side of the graph, because this is forever increasing, the y values approach positive infinity. Okay, so we've done a quick overview of characteristics now. Let's do a quick overview of solving for the SOL test now. So if we're given an equation like this, we haven't talked officially how we solve these. So we're going to solve these by making them a system of equations, much like we did in the quadratics unit. So we're going to take the left-hand side of the equation. We're going to put that into Desmos as the first line. And then we are going to take the right-hand side of the equation, and we're going to put that into Desmos as its own y is equal to line. So let's look at what that looks like. Okay, so I had y is equal to 2 raised to the, in parentheses, x minus 7. That was my left-hand side, and then on my right-hand side, I had y is equal to 8. So when I look at the picture now, I'm going to move my screen around until I can see both lines, and you'll notice we have a horizontal line for y is equal to 8, and we have an exponential growth. The point where these two lines intersect, 10, 8, that x value, x is equal to 10, that's the solution to the equation. So if I'm solving this one graphically, I had my exponential, let's see, it was, what did we just say that was? 10, 8. There's a point up there, and then there was another one at, I think 7, 1 was one of them, and 8, 2. And it had a horizontal asymptote here. So there's a nice sketch of my left-hand side in red, and my right-hand side was that horizontal line at 8. So with that in mind then, that point, 10, 8, is my solution. So because the system of equations, like I said, is 10, 8, x is equal to 10 means that my solution is 10. And I don't have to do all of the work of solving that. So let's look at this next one as well. All right, so I have a logarithm base 2 at this time. So I'm going to type y is equal to, and then in my functions option, I'm going to choose log base a so that I can put a 2 in that base spot. And I'm going to put my x minus 4 in parentheses, and then my left-hand side was y is equal to 1. So again, I have a graph with a horizontal line and a logarithmic growth. Wherever that intersection point is, the red and the black lines in this case at 6, 1, that is my intersection point, which means it is my solution. So I had a horizontal asymptote at 4, or sorry, a vertical asymptote at 4. I had a point at 5, 0, and then whoops, there was another one right after that at 6, 1. Oh goodness, keep touching my keyboard. Okay, and so that was my logarithm side, my left side. My right side, which was that y is equal to 1, is just a horizontal line. And that intersection point, as we saw on Desmos, was at 6, 1, and that x value is 6. Oops, so that's my solution. X is equal to 6. Try and clean that up, or maybe I'll just scribble it out. Okay, so with that, we've learned a lot of little things in this overview. We can tell the difference between exponential and logarithmic growths and decays based on the equation that you're given, based on the asymptote that you can find, and based on that shape. We can figure out the characteristics, the discontinuities like the asymptotes, the domain, range, all those sorts of things. We can use the buttons on Desmos to create logarithms and natural logarithms, and we can solve equations by making a system of equations in Desmos. Go ahead and give those Now You Try problems a shot.